Welcome, everyone. Thank you for joining us for today's webinar, Live Integration of Heterogeneous Data with RapidsDB Federation. My name is Annie Zhu, and I'm the host of today's webinar. Before we begin the presentation, I would like to briefly give you an overview of our company. RapidsDB was founded in 2014. We're specialized in the research and development of big data real-time processing. Our headquarters are in Beijing, China, and Silicon Valley, USA. Currently, we have about 100 global employees. Our core application product, RapidsDB, is a fully parallel, distributed, in-memory federated query system that is designed to support complex analytical SQL queries. The RapidsDB platform helps corporations extract valuable insights from big data and leverage the power of analytics and machine learning to drive sales, make better business decisions, and ultimately transform data into corporate assets. RapidsDB has established several international database standards since 2015. And now I would like to introduce today's speakers, Dave Cracknell and Bev Turnbaugh. Dave is the VP of R&D, and Bev is the QA Director at RapidsDB. They both have worked at some of the world's leading database companies prior to joining RapidsDB, and have extensive experience in distributed databases and analytical technologies. Next, they're going to talk about some of the pain points of data preparation and how the RapidsDB platform takes a unique approach to integrate heterogeneous data with a high-performance database. Welcome, Dave and Bev.
Thank you for that great introduction, Annie. Today's big data environment consists of multiple data sources covering various aspects of the business that need to be combined or consolidated in order to apply analytics to get actionable results. The current methodology for doing this usually involves time-consuming, labor-intensive ETL practices resulting in a data lake. Managing the schema information and object naming across disparate data sources to provide a unified view of the entire data lake is another major challenge. The traditional approach of using ETL to get the data into a common format and location where it can be queried is complex, expensive, and slow, and often results in multiple out-of-date copies of the data that need to be managed. As new data sources become available, the ETL process is in constant flux as new schema information must be accommodated, new processing must be added, and the data lake continues to grow. Even after the challenges of integrating the data, allowing for a flexible enough ETL process to permit the introduction of new and evolving data sources, and designing a malleable data scheme are addressed, there remains one critical challenge: performance. Applying analytics to the data lake that result in clear and actionable results must occur in real time in order to give a business a competitive edge. What if you could avoid the ETL process altogether? What if you could simply pull your data from each source without having to copy it somewhere else? What if you could see your disparate sources as a single schema? What if you could run queries through one source that access all your underlying data stores? What if these queries run against the data in your data stores as those data sources are being constantly updated? The RapidsDB Federation system is uniquely positioned to meet those very requirements. Through the RapidsDB connector system, the RapidsDB execution engine can get access to the data where it resides without the need for ETL or making additional copies of the data. The data is presented to the user as a single federated database where the user can easily identify and combine the data across any of the data sources. RapidsDB Federation system allows 1. Data to stay where data is sourced. 2. A single point of reference for all the data sources by providing a single schema for all connected data sources. 3. RapidsDB execution engine which sees your data as a single entity with the ability to do joins across multiple data sources, multiple tables. 4. The RapidsDB execution engine is a fully distributed in-memory MPP engine that can provide the performance needed to deliver the results in the time frame needed by the business users. And 5. RapidsDB Federation easily allows for the introduction of new data in existing sources or new data sources altogether. How does it do this? By utilizing the RapidsDB federated architecture and the RapidsDB connector system.
This slide shows a complete Rapids data platform, which is comprised of several interconnected components. Rapids Parallel R is a fully distributed parallel implementation of the R engine that is tightly integrated with the RapidsDB query engine to allow the user to run advanced AI algorithms against the federated data sources made available by the RapidsDB query engine. StreamDB is an in-memory streaming data subsystem that is embedded into the RapidsDB database, and it allows the user to combine data from streaming data sources with more static data from other data sources in the federated database. RapidsDB is the distributed, in-memory query execution engine that provides the real-time performance needed when querying across the data sources in the federated database. The Rapids Federation is the connector technology that we're going to discuss in more detail in the rest of this presentation, which provides the RapidsDB execution engine with access to the data sources that make up the federated database. Finally, the Rapids Manager provides a web-based interface for managing the Rapids data platform. This slide shows the components that make up the RapidsDB query engine and how the Rapids Federation connector subsystem fits into this architecture. RapidsDB is a fully distributed, ANSI-compliant MPP in-memory query execution engine. RapidsDB supports a variety of interfaces for submitting queries and has a cost-based optimizer for generating the query execution plans. The MPP execution engine is responsible for execution of the query plans in concert with the Federation connectors that provide the access to the underlying data sources. In the next few slides, we will focus on the Federation connectors and how they control access to the data sources and work cooperatively with the RapidsDB execution engine.
The RapidsDB Federation connectors are a set of dynamically pluggable connectors that control access to the underlying data stores that make up the federated database. The connectors manage the metadata for the objects, typically tables or files, in the remote data store and present that metadata to the RapidsDB query execution engine as an ANSI-based SQL schema, thereby allowing the user to view the objects from the entire set of data sources as a single federated SQL database. Where possible, the metadata will be retrieved using the native definition from the data store. For example, where the data store is a relational database such as Postgres, the schema information will be taken directly from Postgres. If the schema metadata is not available, for example, when accessing a file, the user can provide the schema definition for that file to the connector. The connectors are responsible for managing data type conversion between the native data store and the RapidsDB query system, which allows for the uniform handling of data types across all of the data stores. The connectors present the data to the RapidsDB execution engine as rows and columns, which allows the data to be queried using standard ANSI SQL and provides a uniform query interface regardless of the data source. The connectors access the data from the data store in place without the need for any expensive and complex ETL operations. New connectors can easily be added to support new data sources and data formats as they become available. Connectors are written in Java and can be dynamically added to the system. Users can write their own connectors for access to proprietary data stores. Now let's take a look at some examples of how RapidsDB connectors are configured and used. In this example, we have a Postgres database named DW1, which has two schemas named Customer and Web, which in turn have a set of tables under each schema. In order to access the tables in RapidsDB from the DW1 database in Postgres, we would create a connector as shown here, where we will tell the connector that we want to access all of the schemas in the DW1 database. The PG1 connector will then get the schema metadata for all of the tables and store that metadata in the RapidsDB metastore, as shown here. As you can see, the catalog, schema, and table names are preserved from Postgres so that the user can easily identify those tables in a query. In addition, the column names will also be preserved, and the data types will be converted, if necessary, to the native data type supported by RapidsDB. The user can then query any of these tables using either the unqualified table name, if that name is unique, as shown here, or if the table name is not unique, then the table name can be qualified with either the schema name or catalog and schema names to make the name unique. It should be noted that other systems that can access remote data stores often require the schema metadata to be specified explicitly for each table and do not support the ability to bring across the schema metadata for all of the tables in a catalog or schema. In this example, we want to access a CSV file named daily.csv from HDFS where there is no predefined schema. In order to access this file, we would create a connector as shown here, where we tell the connector the location and format of the file, and then we provide the schema definition to be used for that file. The logs connector in this example would then store this metadata in the RapidsDB metastore as shown here. Note that because this is a simple file, there is no schema or catalog name specified for the file, and so the connector will use the connector name, logs in this example, as the catalog name, and the schema name is set to public. The user can now query the data directly from this file by specifying the unqualified table name associated with this file, daily log in this example. If that table is not unique, then the table name can be qualified with the schema name or catalog and schema names to make that name unique.
In some cases, the user may not want to include all of the available tables from a target data source. Using the previous example from the DW1 database in Postgres, let's say that we're only interested in the tables from the web schema. In this case, we could instruct the connector to only bring in the tables from the web schema as shown here, where we have used the schema option to provide the names of the schemas that we want to include. In this case, it is the web schema. The connector will now only include the tables from the web schema in the RapidsDB metastore as shown here. If the user attempts to access a table from the customer schema, RapidsDB will return an error. The user can now access any of the tables from the web schema as before. In addition to the schema option, the connector also supports a catalog option to allow the user to control access at the catalog level, as well as a table option to control access at the individual table level. The combination of the catalog, schema, and table options provides the user with total control over the tables that a connector will access. It is also possible to add new schema information dynamically. In this example, we are again accessing an HDFS file named daily.csv. But rather than including the schema metadata for this file directly in the connector definition, this time we're going to store the information in an HDFS file and then inform the connector to pick up the metadata information for any files from that HDFS file. In this example, the metadata file is named schema.sql, and it will have the schema metadata for the daily.csv file as shown here. Here is the connector definition. Note the use of the schema metadata option to specify the location of the schema metadata file. As before, the logs connector will store the metadata in the RapidsDB metastore. Now let's say that we create a new file in HDFS named weekly.csv that we want to be able to query. In order to access this file, we simply have to update the schema metadata file with the schema metadata for the new file as shown here. And then we just have to run the RapidsDB refresh connector command as shown here. This will result in the logs connector rereading the schema metadata file and adding the schema metadata for both the daily.csv and weekly.csv to the RapidsDB metastore. The user will then be able to query the newly added table named weekly log as shown here. Here are a collection of data sources that can be accessed as a single federated database from RapidsDB using ANSI standard SQL, regardless of the capabilities of the data source. In this example, we have a query that is going to join the customer table from Oracle with the inventory table from DB2 with the sales.csv file from HDFS. For this example, we would have three connectors: an Oracle connector that would control access to the customer table in Oracle, a JDBC connector that controls access to the inventory table in DB2, and a Hadoop connector that controls access to the sales.csv file in HDFS. In order to execute this query, the execution engine would request data for each of the tables from the three connectors and join the data. The actual query execution uses a streaming data flow model, which is beyond the scope of this webinar. However, one important aspect of this is how can we optimize the performance of this join so that the RapidsDB execution engine is doing the least possible amount of work. RapidsDB solves this problem using a feature called adaptive query pushdown, which we're going to cover in the next two slides. In order to optimize performance, we generally want to have the underlying data source perform as much of the query as possible to reduce the amount of data that has to be processed by the RapidsDB execution engine, rather than simply pulling all of the data from the data source and processing it within RapidsDB. For example, when the data source is a relational database, that data source is typically capable of executing a join on the tables in that data source, or it can filter the data based on predicates in the query. RapidsDB supports an optimization feature called adaptive query pushdown to deal with this. With adaptive query pushdown, each connector involved in the execution of a query plan analyzes the query plan and decides which parts of that query plan it can push down to a data source or handle within the connector. In this example, we have a four-way join where two of the tables, customer and address, are in Oracle. The inventory table is in DB2, and the sales.csv file is in HDFS. After analyzing the query, the Oracle connector determines that it can push down the join of the customer and address tables to Oracle, so that RapidsDB has to only then join the results of that query with the inventory and sales tables. The RapidsDB execution engine will then perform the join using the results of the join from Oracle and then complete the joins to the DB2 table and the HDFS file. Let's look at the previous example, but this time let's take a closer look at how the Hadoop connector can make use of adaptive query pushdown. In the case of HDFS, there is no intelligent engine to push the query to. But if the sales data was partitioned on the state column and the data was in Parquet format, then the Hadoop connector can use that information to only read the data from the files where the partition name matches the predicate in the query, state equals CA in this example. Furthermore, because the files associated with this table are in Parquet format, the Hadoop connector can use the predicate salesman equals Rivera to filter the Parquet data, thereby minimizing the amount of data that gets returned to the RapidsDB execution engine. So this is an example of where adaptive query pushdown can be used within the connector rather than actually pushing the query down to the underlying data source.
The next two slides show two use cases where RapidsDB Federation is being used. In this first example, we have a banking customer where the business user is getting a holistic view of business data and the customer profile. In this use case, DB2 contains hot and warm data, which can be joined with the full history data on HDFS, so that the business user can have a clear view about how the business and customer change in real time. The user can perform ETL operations directly using RapidsDB. Federated queries allow customers to filter out unneeded data on demand and only transfer required data into the RapidsDB analytical data store for further analysis. With the RapidsDB Data Federation, this can be done at any time and can be changed dynamically at any time.
This is a telco use case. Within the call center, RapidsDB is able to connect to and query various heterogeneous databases in the customer organization using standard ANSI SQL. While call center staff are still able to continue their current data consolidation process with help from ETL, call center customer representatives have a chance to conduct ad hoc queries using data from all the available data sources to answer consumer questions in real time and to gain in-depth knowledge about critical consumer questions. With the telco network, the huge volume of telco network data can provide valuable insights into the behavior of the network and users on the network. The problem is that it is hard to analyze such large volumes of data at such velocity with traditional database technology. The Rapids Data StreamDB streaming engine allows real-time analysis to be done against the streaming network data in real time. By joining the streaming data with more static data like the customer data, the analyst can then gain valuable insights in real time.
So let's review the advantages of RapidsDB Federation. RapidsDB Federation delivers a system that allows data to be queried in place without the need for ETL. RapidsDB Federation delivers a system that can query and combine data across a wide variety of data sources. RapidsDB Federation delivers a system that can provide a single database with uniform naming across all of the needed data sources. RapidsDB Federation delivers a system that can easily support and include new data sources as they become available. RapidsDB Federation delivers a system that can meet the performance requirements to deliver results quickly and easily.
Thank you, Dave and Bev. And thank you, everyone. We appreciate your time watching this video. For those of you with questions or want to get in touch with us, please email us at info@rapidsdata.com. Our experts will answer your questions as soon as possible. We invite you to learn more about Rapids Data Platform at rapidsdb.com. Again, thank you for joining us today and have a great remainder of the day.